Having seen the power of non-determinism in designing this PDA, let's formally describe. So starting from Q0, reading 0, stack symbol is Z0, we go to Q1, we push A. And being in Q1, I read a 0 with stack symbol being A, we push one more A. So this takes care of push. Now we are at Q1, we read a 1, top of the stack is A. Now we take a call whether to pop this or skip and pop the next one. Either this or we skip, which means top of the stack is still A. Now I am in Q2, read 1 A. So here again we either pop or skip and read the next one. So this part ensures pop A either for 1 or 1 1. For the second one, if we pop, which means for the first one we skip. This is pop, this is skip. Fine. So this part is skip, this one is pop. And we have seen that there will be at least one sequence of moves starting from here, which will take us to the valid configuration if it is a valid input. So I am in Q2, exhausted the input, and stack contains Z0, which means it's a valid input. We say reach the final state and stop the mission. So if you look at the transition diagram, it says Q0 on reading 0, stack contains Z0, we reach Q1 and push A onto the stack. It becomes A Z0. And being in Q1, you continue to read some more zeros and push one more A. Now with this, we would have pushed N A's. Now we start performing pop or skip. We read 1, top of the stack as A in it, we pop and reach Q2, or we say 1 comma A, do nothing, skip that 1 and reach Q2. Now I am in Q2, you read 1, stack contains A, you perform pop, or 1 A, do nothing and retain that A as it is, which means we are skipping this one and moving to the next one. Now everything goes well, we exhaust the input, top of the stack contains Z0, we reach the final state. Now at some point in time, you get to see that either there is a 1 at the start or there is a 0 from here, you move to QR. These two I have not described here, but it's very similar to what we have described so far. So this clearly tells you that non-determinism happens over here. On reading 1, seeing A, should I pop or skip and go here? If you skip and you come over here, for the second one you pop. Okay, and because of that we see that this design is inherently brings non-determinism, and this language can only be solved through a non-deterministic push-down automata. And as we have seen before, suppose you take the input to be 0, 0, 1, 1. To start with, it is Z0, then we perform 2 push operation, then we see 1. One direction says you perform pop, so 1A is out. Okay, so pop, and then input pointer is here. The next one says you also pop this and pointer is here, or it says you skip and go to the next one, and when you go to the next one you perform pop. Okay. Now this sequence is invalid, but here is a sequence in which you see that you are here, you have performed 1 pop and then skip and then pop for this, which means input is exhausted, stack contains Z0, that's valid, so you accept this string. So there is at least one sequence of moves starting from Q0 taking me to the final state, and you accept the input. Fine. Now, as always, one can look at the context-free grammar. So the simplest patterns are 0, 1 or 0, 1, 1. Then recursion with the help of these two, 0, S1 or 0, S, 1, 1. Let's look at string like this. So I start with 0, S, 1, 1. Then I want to terminate, choose this, then it becomes 0, 0, 1, 1, 1. Remember, you keep using this, we get 0 power n, 1 power n. You keep using this, you get 0 power n, 1 power 2n. Now if you mix these two, then we get to see this. The number of ones we generate is between n and 2 power n. So 0 S1 gives you 0 power n, 1 power n, and 0 S11 gives you 0 power n, 1 power 2n. Now it is S on both, which means this can be plugged in this as well. Means you get to see 0, 0, 1, 1, then 3, 0, 5 ones, and which means you get to see that number of ones is between n and 2 power n. Correct? This will act as a lower bound, this will act as upper bound. When you plug in here, you get to see number of ones between this lower bound and this upper bound. That's precisely what we have done. This is an interesting case study wherein we brought non-determinism into the design, and which is inevitable. One cannot come up with a deterministic equivalent. One cannot come up with an equivalent deterministic PDA for this, and so non-determinism is inevitable in this case. And we also see why non-determinism is useful in designing such automatons. and you may have to take a guess or a call whether to take this direction or this direction. But as far as the acceptance is concerned, there should be at least one sequence of moves taking me to this sequence of moves is deterministic in nature. This sequence of moves is deterministic in nature. But at this point in time, machine takes a guess. Should I take this branch or this branch? That's where non-determinism comes into the picture. And as always, we designed the machine using transition function, diagram, and context-free grammar. Now let's try understanding the limitations of these machines. So like this, what more it can compute, what is that it cannot compute, all that we shall discuss next.